Let me start with a question that seems incredibly simple. In C++, where exactly does the this pointer point? Most people will answer without hesitation. It points to the current object. This answer seems correct in many cases. Even when you check with a debugger, you'll almost always see that this matches the object's address perfectly. But today, I want to tell you, this understanding is dangerous and technically incorrect from a language standard perspective. The this pointer is not guaranteed to point to the start address of an object. In some cases, it's actually deliberately designed to point elsewhere. Let's start with the most basic example to see how this illusion is formed. When you run this code, you'll see that the object's address printed on the console is exactly the same as the this pointer. You naturally form a mental model like this. An object A has an address in memory. When you call foo function, this equals the address of A. Indeed, in scenarios with single inheritance and no virtual functions, compilers pass the object start address as the this pointer to member functions, so this model holds true. But here's the critical point. This is merely a common compiler implementation, not a requirement of the C++ standard. The C++ standard has never promised that the this pointer must point to the object's start address. It just happens to be implemented this way in most cases. And once your code involves complex scenarios like multiple inheritance or virtual functions, this perfect illusion shatters instantly. Let's look at a typical multiple inheritance case, which exposes the true nature of the this pointer most clearly. In mainstream compilers like GCC and Clang, the memory layout of a derived class in multiple inheritance arranges base class subobjects and its own members in the order of inheritance. In other words, the memory layout of object obj is exactly like what's on your screen. To put it simply, the A subobject starts at offset 0, which is exactly the start address of the entire object. The B subobject starts at offset 4 bytes away from the entire object's start address. The C class's own member C starts at offset 8 bytes. When you run this code, you'll see a result that defies your expectations. The this pointer is not the same everywhere. When calling obj.function A, the this pointer matches object's address exactly. It's the start address of the object. When calling obj.function B or pb arrow function B, the this pointer is no longer equal to object's address. Instead, it's object's address plus 4 bytes, pointing exactly to the start address of the B subobject. Why does this happen? Because the compiler does something invisible behind the scenes. It automatically adjusts the value of the this pointer. Let's think about this question. In B double colon function, where should this point? It can't point to object's address, right? Because the B subobject doesn't start at the beginning of the entire object. So the correct answer is, this must point to the start address of the B subobject. This is the key to understanding everything. This is not a fixed address. It's simply a hidden parameter passed to the function. And parameters can be modified by the compiler. Taking the call to function B as an example, the assembly code generated by the compiler looks roughly like this. From the perspective of this function, it never knows the existence of the original object obj at all. This pointer it receives is already adjusted by the compiler to point to the B subobject. From the function's internal perspective, this pointer is completely correct. It points to the object it belongs to. This leads us to today's core conclusion. This pointer is not a fixed object address. It's merely a hidden parameter dynamically adjusted by the compiler based on the calling context. It never points to the entire object, but rather to the specific subobject that the current function belongs to. When virtual functions are added to multiple inheritance, things get even more complex. In single inheritance, a class usually has only one virtual table. But in multiple inheritance, the derived class C has multiple virtual tables, one corresponding to the A subobject and one corresponding to the B subobject. This is because when calling a virtual function through an A pointer, this needs to point to the A subobject. When calling through a B pointer, this needs to point to the B subobject. The virtual tables for the two subobjects must be separate to ensure the correctness of the this pointer during virtual function calls. But the more critical point is, what's stored in the table is not the direct address of the functions we write, but rather compiler-generated thunk functions. A thunk is an extremely small function that does only two things. First, adjusts the this pointer to correct it to the start address of the current subobject. Second, jumps to the actual function implementation. Taking this call as an example, the complete execution flow is as follows. Through the pd pointer, find the virtual table corresponding to the B subobject. Retrieve the address of the thunk function from the virtual table. Execute the thunk function, adjusting the this pointer to the address of the B subobject. The thunk function jumps to the actual implementation of the thunk function. This is why under multiple inheritance, the number of virtual tables increases and the virtual function call path is more complex than we imagine. Every virtual function that requires this pointer adjustment has a dedicated thunk function corresponding to it. At this point, some of you might be asking, these low-level details aren't used in daily development, right? Does it matter whether we know them or not? If you've ever done any of the following, I want to tell you seriously, you've already stepped into a minefield of undefined behavior, and your misunderstanding of the this pointer is the fuse that can detonate these mines. Casually casting the this pointer with reinterpret_cast. For example, in a base class member function, force casting this to a derived class pointer while ignoring potential offsets of this directly leads to memory access errors. Assuming this equals the address of the most-derived object. In a base class function, taking it for granted that this points to the entire derived object and directly accessing derived class, members through this will inevitably cause errors in multiple inheritance scenarios. Performing pointer arithmetic based on this line of code completely relies on a fixed object layout, which the C++ standard has never guaranteed to be stable. Serializing objects via memory dumps, writing the binary memory of an object directly to a file depends on the compiler's memory layout. Switching compilers or platforms will render the serialized data completely invalid. Relying on object layouts across ABI boundaries, for example, in cross-module calls, if the compilers on both sides implement object layouts differently, the past this pointer will cause the program to crash directly. These scenarios may seem niche, but once problems occur, they are extremely difficult to troubleshoot. Because from a code perspective, everything looks perfectly reasonable, but the underlying this pointer offsets make the program's behavior completely unpredictable. The C++ standard does not guarantee object layouts, does not guarantee base class offsets, and certainly does not guarantee that this points to the entire object. This is context dependent, not absolute. Here's a fact that many people have never truly considered. C++ member functions are essentially just ordinary global functions, with one hidden parameter automatically added by the compiler. This parameter is generated by the compiler, governed by ABI conventions, and dynamically adjusted to support inheritance and polymorphism. Once you accept this fact, many previously confusing issues become clear. The memory layout of multiple inheritance is no longer mysterious. It's essentially the compiler's precise adjustment of the this pointer. The virtual function call path becomes clear. The thunk mechanism exists solely to solve the problem of this pointer adjustment. The importance of ABI comes to the forefront. It's the core rule that dictates how compilers implement these low-level details. And it's truly the low-level boundary of C++. So the next time you hear someone say, this pointer is just the object's address, you can smile and ask in response, which object and at what offset? In the next video, we'll continue along this line of thinking to explore why the true boundary of C++ is ABI, not the language itself. See you next time.